Hello. In this course, you will explore how to create serverless applications. You will start off by looking into the Azure developer role and getting an overview of the entry-level jobs and possible career paths. You will explore how to automate your business processes with Microsoft Azure. Then you will get hands-on experience on how to use triggers to determine how an Azure function is executed. You will also learn how to chain Azure functions together using input and output bindings. Next, you will explore how to modernize workflow with Azure Functions by creating a long-running serverless workflow with durable functions. You will also have a chance to develop, test and publish Azure Functions by using Azure Functions core tools and Visual Studio. Then you will practice monitoring GitHub events by using a webhook with Azure Functions, creating a function triggered by a webhook. Next, you will explore enabling automatic updates and build APIs using Azure Functions and SignalR service. You will also learn how to expose multiple Azure Function apps as a consistent API by using Azure API Management. Finally, you will have an opportunity to recap what you've learned and take a practice exam. Becoming a Microsoft Certified Azure Developer Associate is an exciting career, and obtaining the AZ-204 Developing Solutions for Microsoft Azure certification can be the first step in preparing you for your next job as an Azure developer. Responsibilities for an Azure developer professional include participating in all phases of cloud development, from requirements, definition and design, to development, deployment and maintenance, to performance tuning and monitoring. Azure Functions offers support for various languages, including C#, JavaScript and F#. So to become an Azure developer, you should have experience programming in these languages. It is also expected that Azure developers have experience with other technologies, including ASP.NET, SQL Server and Visual Studio. Azure developers have a wide range of paths they can choose to focus on, such as developing for cloud storage, creating PaaS solutions, IaaS solutions, artificial intelligence and security. You might be wondering about following a career in this field and how to move in that direction. Let's take a look at 3 examples of people who decided to pursue a career as an Azure developer. Let's start with Letitia. Letitia has a degree in computer science and over 5 years' experience as a developer. Letitia is looking for ways to advance in her career field and upskill in a competitive work environment. Letitia wants to add new credentials to her portfolio and step beyond data processing into building cloud solutions that drive business growth. And to do so, she plans to become a Microsoft Certified Azure developer. Now let's turn to Frank. Frank has over 3 years of experience working as a developer. He is a beginner in Microsoft Azure. Just like Letitia, Frank wants to move forward in his career and upskill in a competitive work environment. Frank is familiar with the cloud data services available from Google and AWS, but is looking to add foundational knowledge of developer services in Microsoft Azure. Finally, let's take a look at Jose. Jose lost his job during the COVID crisis. He has a master's degree in computer science and 15 years of experience working as a software tester. Jose wants to enhance his tech skills and learn more about developing cloud services so he can switch his career and become an Azure developer. As Jose passes the Microsoft AZ-204 exam, he will be one step closer to achieving his professional goal. He will then be able to start his career as a Microsoft Certified Azure Developer Associate. Letitia, Frank and Jose all know that a Microsoft certification will help validate that they stay ahead with today's technology. They also know that their studies will boost their confidence and give them renewed job satisfaction. You can see that these people coming from a different background have chosen to pursue a Microsoft certification path that matches their career aspirations while improving their skills. There are different certification paths for you to choose from depending on your expertise and background. The certifications are structured into 3 expertise levels. The fundamentals certifications are targeted towards those just starting out with the technologies covered or looking to change careers. The associate certifications are targeted towards professionals that already have at least 2 years of practical experience working with the technologies covered. And the expert certifications are targeted towards professionals that have a minimum of 5 years advanced levels of practical experience and skills with the technologies covered. We have provided links to the various Microsoft certifications at the end of this lesson so that you can explore them in more detail. Obtaining the Microsoft Azure Developer Associate certification can help you jumpstart your career as an Azure developer. It also prepares you to dive deeper into the many technical opportunities Microsoft Azure offers. This certification is an opportunity to demonstrate your ability to create end-to-end solutions in Microsoft Azure. This certification is intended for candidates who have 1 to 2 years professional development experience and experience with Microsoft Azure. Taking the exam AZ-204, Developing Solutions for Microsoft Azure, is the right choice if you want to become a Microsoft Certified Azure Developer Associate. In the Microsoft AZ-204 exam, there will be 40 to 60 questions. There are different question types used during the exam, including scenario-based, single-answer questions, arranged in the correct sequence, drag and drop, mark review, and so on. To obtain the Microsoft Azure Developer Associate certification, you will need to pass the AZ-204 exam, which covers the following topics with varying weights. Develop Azure Compute Solutions, develop for Azure Storage, implement Azure Security, monitor, troubleshoot and optimize Azure solutions, and connect to and consume Azure services and third-party services. At this point, you may be wondering if you will have access to the information that you'll need to successfully pass the AZ-204 Developing Solutions for Microsoft Azure exam. The answer is yes. Each domain area is mapped to this program. You will be awarded a Coursera certificate for each course and graded quiz you successfully complete. You will also receive a certificate on successful completion of this program. Next, you'll receive an electronic notification that allows you to unlock a 50% discount certification voucher code. Once you have unlocked the code, we encourage you to register and schedule the exam. You will be given directions on how to do this and how to prepare for the exam. Good luck with your preparation. Hello and welcome to this lesson, where you will learn how to choose the best Azure service to automate your business processes. Modern businesses run on multiple applications and services. How well your business runs can often be impacted by how efficiently you can distribute the right data to the right task. Automating this flow of data can streamline your business even further. Choosing the right technology for these critical data integrations and process automation is also an important consideration. Suppose you're a developer at a company that operates a bike rental system at a large state university. Your company recently acquired the rights to operate at another university in the next state. The other university also has a rental system in place. You'll need to integrate with those existing systems too. The systems include bike tracking, inventory management, rental scheme registration, and more. It's June, and the university would like to have the rental system in place before students arrive on campus in late August. Your business runs on Microsoft Azure, and a requirement of this integration is that you don't take on any infrastructure maintenance or heavy upfront costs. As you expand into other universities across the country, you need to be able to scale efficiently in order to keep costs down and your low margins viable. In this lesson, we'll describe the Azure technologies that are available to you and teach you how to evaluate each one for your business needs. Upon completion of this module, you'll be able to evaluate Microsoft Azure services for integration and process automation scenarios. You don't have much time to get business processes properly integrated between your existing bike rental system and the system in use in the second campus. You'd like to make the most of your existing Azure expertise, and you've read that Azure includes several different technologies that you can use to solve problems like this. Now we'll explore the Azure technology options that are available to automate and integrate your business processes. In business, one way to guarantee a high-quality service to users and high-quality products is to design and implement strict business processes. Such processes may involve multiple steps, multiple people, and multiple software packages. Each process may run in a simple line of activities that workers perform one after the other, or they may branch or loop. Each process may also run quickly or take days or weeks to complete. Frequently, a business runs into issues when it merges with a second business or integrates with a partner organization. How can administrators integrate the separate processes used in the two organizations, which may have been implemented using different software? Business processes modeled in software are often called workflows. Azure includes 4 different technologies that you can use to build and implement workflows that integrate multiple systems: Logic Apps, Microsoft Power Automate, Web Jobs, and Azure Functions. These four technologies have some similarities. For example, they can all accept inputs. An input is a piece of data or a file that is supplied to the workflow. They can all run actions. An action is a simple operation that the workflow executes and may often modify data or cause another action to be performed. They can all include conditions. A condition is a test, often run against an input, that may decide which action to execute next. And they can all produce outputs. An output is a piece of data or a file that is created by the workflow. In addition, workflows created with these technologies can either start based on a schedule or they can be triggered by some external event. When business analysts discuss and plan a business process, they may draw a flow diagram on paper. With Logic Apps and Microsoft Power Automate, you can take a similar approach to designing a workflow. They both include user interfaces in which you can draw out the workflow. We call this approach a design-first approach. Logic Apps is a service within Azure that you can use to automate, orchestrate, and integrate disparate components of a distributed application. By using the design-first approach in Logic Apps, you can draw out complex workflows that model complex business processes. The Logic Apps Designer and Design Canvas can be used to define your workflow. Alternatively, if you prefer to work in code, you can create or edit a workflow in JSON notation by using the code view. One reason why Logic Apps is so good at integration is that over 200 connectors are included. A connector is a Logic Apps component that provides an interface to an external service. For example, the Twitter connector allows you to send and retrieve tweets, while the Office 365 Outlook connector lets you manage your email, calendar, and contacts. Logic Apps provides hundreds of pre-built connectors that you can use to create your apps. If you have an unusual or unique system that you want to call from a Logic Apps, you can create your own connector if your system exposes a REST API. Microsoft Power Automate is a service that you can use to create workflows even when you have no development or IT pro experience. You can create workflows that integrate and orchestrate many different components by using the website or the Microsoft Power Automate mobile app. There are 4 different types of flow that you can create. Automated, a flow that is started by a trigger from some event. For example, the event could be the arrival of a new tweet or a new file being uploaded. Button, use a button flow to run a repetitive task with a single click from your mobile device. Scheduled, a flow that executes on a regular basis, such as once a week, on a specific date, or after 10 hours. Business process, a flow that models a business process, such as the stock ordering process or the complaints procedure. The flow process can have notification to required people with their approval recorded, calendar dates for steps, and recorded time of flow steps. Microsoft Power Automate provides an easy-to-use design surface that anyone can use to create flows of these types. The designer makes it easy to design and lay out your process. Under the hood, Microsoft Power Automate is built on Logic Apps. This means that Power Automate supports the same range of connectors and actions. You can also use custom connectors in Microsoft Power Automate. Microsoft Power Automate is more appropriate for use by non-technical staff. If your workflow designers are IT professionals, developers, or DevOps practitioners, Logic Apps are usually a better fit. Microsoft Power Automate is intended for office workers and business analysts, while Logic Apps is intended for developers and IT pros. Additionally, Power Automate is suited for self-service workflow creation, whereas Logic Apps is better suited for advanced integration projects. Microsoft Power Automate offers a graphic user interface only on a browser and mobile app. On the other hand, Logic Apps is available on a browser and Visual Studio Designer. Code editing is also possible. Finally, as far as application lifecycle management, Power Automate includes testing and production environments. And Logic Apps source code can be included in Azure DevOps and source code management systems. You should now be well equipped to decide which design-first technology you should choose when designing your workflow. The developers on your team will likely prefer to write code when they want to orchestrate and integrate different business applications into a single workflow. This is the case when you need more control over the performance of your workflow or need to write custom code as part of the business process. For such people, Azure includes web jobs and functions. The Azure App Service is a cloud-based hosting service for web applications, mobile backends, and RESTful APIs. These applications often need to perform some kind of background task. For example, in your bike rental system, when a user uploads a photo of a bike, you may need to generate a smaller thumbnail photograph. Web jobs are a part of the Azure App Service that you can use to run a program or script automatically. There are two kinds of web job. The continuous web jobs run in a continuous loop. For example, you could use a continuous web job to check a shared folder for a new photo. The triggered web jobs run when you manually start them or on a schedule. To determine what actions your web jobs takes, you can write code in several different languages. For example, you can script the web job by writing code in a shell script, such as Batch, PowerShell, or Bash. Alternatively, you can write a program in PHP, Python, Node.js, or JavaScript. These web jobs do have a few limitations, such as only supporting ASP.NET SDK 2.x. However, SDK 3.x supports .NET Core. You can also program a web job by using the .NET Framework or the .NET Core Framework and a .NET language such as C# or VB.NET. In this case, you can also use the Web Jobs SDK to make the task easier. The SDK includes a range of classes such as Job Host Configuration and Host Builder, which reduce the amount of code required to interact with the Azure App Service. The Web Jobs SDK only supports C# and the NuGet Package Manager. An Azure function is a simple way for you to run small pieces of code in the cloud without having to worry about the infrastructure required to host that code. You can write the function in C#, Java, JavaScript, PowerShell, or Python. You can also write functions in any of the languages that are listed in the Supported Languages in Azure Functions article, which is linked to in the additional reading section at the end of this lesson. In addition, with the consumption plan option, you only pay for the time when the code runs. Azure automatically scales your function in response to the demand from users. When you create an Azure function, you can start by writing the code for it in the portal. Alternatively, if you need source code management, you can use GitHub or Azure DevOps Services. To create an Azure function, choose from the range of templates. The following list is an example of some of the templates available to you. You should use the HTTP trigger template when you want the code to execute in response to a request sent through the HTTP protocol. Use the timer trigger template when you want the code to execute according to a schedule. You should use the blob trigger template when you want the code to execute when a new blob is added to an Azure storage account. And finally, use the Cosmos DB trigger template when you want the code to execute in response to new or updated documents in a NoSQL database. Azure Functions can integrate with many different services, both within Azure and from third parties. These services can trigger your function or send data input to your function or receive data output from your function. In most cases, the simple administration and more flexible coding model provided by Azure Functions may lead you to choose them in preference to web jobs. However, you may choose web jobs for the following reasons. You want the code to be a part of an existing app service application and to be managed as part of that application, for example, in the same Azure DevOps environment. You need close control over the object that listens for events that trigger the code. This object in question is the job host class, and you have more flexibility to modify its behavior in web jobs. In terms of supported languages, Azure Web Jobs supports C# if you are using the Web Jobs SDK. On the other hand, Azure Functions supports C#, Java, JavaScript, PowerShell, and many more. Azure Functions also supports automatic scaling, development and testing in a browser, pay-per-use pricing and integration with Logic Apps, whereas Web Jobs does not. Additionally, Web Jobs supports NuGet if you are using the Web Jobs SDK, while Azure Functions supports both NuGet and NPM. However, Web Jobs can be part of an app service application, but Azure Functions can't. And finally, Web Jobs provides close control of job host, whereas Azure Functions does not. Now that you know what design-first and code-first technologies are available to you, how do you narrow your choices? We'll look at this question next. There are several different business processes that run your bicycle rental business. For example, there is the bike rental process, a bike booking process, a return process, and processes that don't directly relate to bikes, such as holiday booking for the staff. We've introduced an array of Azure technology that could be used to help build these processes. Let's try to be more concrete about how we make the decision for a given process. Now let's take a look at how to choose the best technology to use for your business process. When deciding how to choose a service, the first question to ask is whether you prefer to design the workflow in a graphic user interface designer tool or by writing code. You should consider using a design-first tool if people who design the workflow have no coding experience. Or if later you want to allow designers and users to consult the graphical design to clearly understand how the workflow proceeds. Alternatively, you can choose to use a code-first tool if people who design the workflow are developers and prefer to work entirely in code, or if you want the details of a workflow to be hidden from non-coders. You can use a simplified flowchart to choose the best technology to use for your business process. If you choose to use a design-first approach, then you must also choose from Microsoft Power Automate and Azure Logic Apps. The principal question here is who will design the workflow? Will it be developers or users? In Logic Apps, there is a GUI designer on which you draw out the workflow. It is intuitive and easy to use, but you also have the opportunity to delve under the hood and edit the source code for a workflow. This tool is designed for people with development skills. In Microsoft Power Automate, extra help and templates are provided for common types of workflow. There is no way to edit the source code that the tool creates. This tool is designed for users who have a good understanding of the business process but no coding skills. On the other hand, if you choose to use a code-first approach, your next choice is between web jobs and Azure Functions. There are two situations in which web jobs might be a better choice. The first one is if you have an existing Azure App Service application and you want to model the workflow within the application. This requirement means that the workflow can also be managed as part of the application, for example, in an Azure DevOps environment. The second situation is if you have specific customizations that you want to make to the job host that are not supported by Azure Functions. For example, in a web job, you can create a custom retry policy for calls to external systems. This kind of policy can't be configured in an Azure function. Keep in mind that web jobs only support C# on Microsoft Windows. Azure Functions offers extra features, including wider ranges of trigger events and supported languages, the ability to develop test code in the browser, and the pay-per-use price model. Because of these extra features, you should consider Azure Functions to be your default choice. Remember that there is no requirement for you to use the same technology for different workflows. If your requirements differ, you are likely to reach a different answer at the end of your decision-making process. Furthermore, you can also call one workflow from another. For example, a workflow implemented in Microsoft Power Automate can easily call another that is built as an Azure function. One reason to mix the technologies used in your business processes would be to give users control over a small section of a complete workflow. Do this by implementing that section in Microsoft Power Automate, then call that flow from a Logic app, web job, or functions. You want to choose a technology to automate the booking process for your bike rental business. You also want to streamline and modernize this process as it is performed on your original campus. You also want to integrate a bike tracking technology that is used on the new campus where you've recently obtained the rights to operate the existing bike rental business. Now we'll examine this scenario in detail and choose which technology to use. On your original campus, you have 5 bike rental shops. Each shop has a list of bikes for rent and its own database that records the bikes and their features and whether they are already rented or in the shop. Currently, each bike can only be rented from its home shop. When a customer returns a bike to another shop, your staff move it back to the shop where it is listed on the database. You'd like to change the process so that each bike can be rented from any shop. However, you want to ensure staff can find out quickly where each bike is. At the university in the next state, the bike rental business invested in a third-party system to track bike locations. When a bike arrives back at a store, a unique barcode on the crossbar is scanned. The bike tracking database is automatically updated with the name of the shop that scanned the barcode. When a bike leaves a shop with a customer, the location is changed to On Hire, and the customer name is recorded in a separate column. This system has proved helpful when a customer asks for a bike with specific frame size or specific features, such as an electric motor or all-terrain suspension. If a shop doesn't have a bike with the right equipment, the shop can quickly find out where such a bike is and get it, or send the customer to the right shop. This bike location database has a REST API that you can call from other systems. Your managing director wants to be able to understand clearly the workflow that you develop. There were problems in the past when documentation has not been kept in sync with custom code, and your director wants to see the process as it's implemented. Now you want to update the bike reservation and rental process on both campuses to the following workflow. The process starts when a customer requests a bike on the phone, in person or through the website. Then shop staff record the customer's details and frame size. The first decision point is to find out whether the customer needs specific features such as an electric motor, suspension or a child trailer. If the customer doesn't need specific features, the shop staff simply look up bike locations. But if the customer needs specific features, what are those features? The specific features are then recorded and the shop staff look up bike locations. So where are all the bikes with that frame size and the features the customer wants? This information is obtained from the bike location database and is kept up to date by the barcode scanning system. The next step is to check if there is a bike with the right features and frame size in the right shop. If yes, then book that bike. If not, then identify where the nearest bike is and reserve that bike. Send an email to staff to move the bike to the customer and scan barcode in the new location. After booking the bike, then give the bike to the customer and update the location to on hire. Finally, take payment from the customer. This is a simplification of the entire process. For simplicity, we've omitted edge cases such as no bike with the desired frame size or features is available for rent. Perhaps you can think of other cases not covered by this simplified process. We already touched on the Azure technologies available to implement the business process and integrate with the bike location database. They are Azure Logic Apps, Microsoft Power Automate, Azure App Service Web Jobs, and Azure Functions. You could use any of these technologies and others to build a workflow for this business process. Each technology can also integrate with any REST API, so you could also use any of these technologies to integrate with the bike location system. How then can you choose? We know that your managing director and her staff want to understand the workflow at a higher level than examining the code and implementation. She also doesn't like separate documents describing a process because it so easily becomes out of date when the process changes. If you choose a design-first approach, the workflow is visualized in an easy-to-understand design surface. In addition, that diagram is not a separate document, but a picture of the process as it is implemented. The benefit is that there's no possibility that the diagram is not updated when the process is changed. For this reason, choose a design-first approach. Now you must choose from the two design-first technologies, Azure Logic Apps, Microsoft Power Automate. There's no suggestion in the scenario that shop staff should be able to modify the business process. In addition to connect to the bike location database through its REST API, you will need to create a custom connector. This is a developer task. It seems sensible that the development of the custom connector and the workflow should be done by the same person or team. Since these must be developers, it's best to use Azure Logic Apps. As this exercise shows, we can narrow down the technology to use for a given solution by simply understanding the business process and the audience. Now let's look at another process from our bike rental business and decide what technology best fits our needs. We'll consider the technical aspects of the process as well as audience and how our process needs to evolve. In this next scenario, your bike technicians currently use a spreadsheet to record the actions they took to repair and maintain each bike. Difficulties have arisen when spare parts are needed because the staff have no way of knowing when a bike is waiting for repairs or parts. This problem has resulted in bikes being rented to customers with worn brake pads, flat tyres and other faults that may damage the company's brand as a high-quality bike rental company. You want to build a system that governs the maintenance and repair process and allows everyone to find answers to the following questions. What jobs have been completed on a bike? What jobs remain to be completed before the bike can be rented out again? Which bikes are currently available to rent and which bikes are currently unavailable to rent? And for each bike that is unavailable, you need to know, why can't we rent them out? Are we waiting for any parts and what are those parts? And when is the bike likely to be available again for rent? You'd like to integrate this system with the bike booking and rental process from the last unit. In doing so, when shop staff search for available bikes, they find only those bicycles that are currently available to rent. Your manager has asked you to be the developer on this project. You want to ensure that bike technicians on both campuses stick to the following workflow when they maintain a bike following a rental. When a customer returns a bike to any location, the bike maintenance process starts. Then, a technician marks the bike as unavailable. A technician completes a full list of checks, including the tyres, brakes, drive chain, and lights. Then the technician checks if new parts are needed. If new parts are needed, the technician checks if they're in stock. If they aren't, then they need to order new parts. And when the new parts arrive, the technician fits them. But if the required parts are in stock, they simply fit the parts and complete the final adjustments. If new parts are needed, the technician checks if they're in stock. If they aren't, then they need to order new parts. And when the new parts arrive, the technician fits them. But if the required parts are in stock, they simply fit the parts and complete the final adjustments. And if new parts aren't needed, then the technician marks the bike as available for rent. To implement the business process and integrate with the bike location database, let's consider the following set of technologies: Azure Logic Apps, Microsoft Power Automate, Azure App Service Web Jobs, Azure Functions. As in the previous scenario, any of these technologies could be used to build the workflow. However, there are two issues that determine the optimal choice. To implement this workflow using just Logic Apps or Power Automate would be difficult. While we haven't heard too many low-level details, it's clear that this process needs to access an inventory system and place orders with a third-party parts company. This is new business logic, and there is no requirement that we consider a design-first approach. We can wrap our solution in a custom connector to integrate with other workflows created with Logic Apps or Power Automate. As a developer, you have most flexibility by approaching this scenario from a code-first approach, so let's do that. Now we have to make a decision between Azure Functions or Azure App Service Web Jobs. Cost and integrations will influence your decision. As far as cost, with web jobs, you pay for the entire VM or app service plan that hosts the job. Azure Functions can run on a consumption plan, so you only pay when the function runs. Since this process only kicks off when a bike is returned, we might stand to save by selecting Azure Functions. Now let's look at integration. You want to integrate the maintenance workflow with the Logic app that you built earlier for the bike booking and rental process. Although it is possible to call a web job from a Logic app, the integration between Logic apps and functions is closer. For example, you can more easily control your call to a function from the Logic apps designer. For these reasons, we'll select Azure Function to manage your bike maintenance business process. Recapping what you covered in this lesson, you can see that some business processes are simple, but often they include challenges such as they might involve many different steps, sometimes with loops or conditional branches. They may be long-running and complete over days or weeks as staff become available or because of other delays. They may involve several different systems such as databases, web services, email servers, and other components. You may want to integrate a custom or third-party system, which may require a custom connector. You may want non-developers to be able to modify and update the workflow. As you have seen, Azure includes the following technologies that you can use to overcome these challenges: Azure Logic Apps, Microsoft Power Automate, Azure App Service Web Jobs, and Azure Functions. Your choice of technology depends on whether you prefer a design-first or a code-first approach, and whether you have skilled developers to work on the project. Hello and welcome to this lesson, where you'll learn how to create serverless logic with Azure Functions. Imagine you work for an escalator company that has invested in IoT technology to monitor its product in the field. You oversee the processing of temperature sensor data from the drive gears of the escalators. You monitor the temperature data and add a data flag to indicate when the gears are too hot. In downstream systems, this data helps determine when maintenance is required. Your company receives sensor data from several locations and from different escalator models. The data arrives in different formats, including batch file uploads, scheduled database pulls, messages on a queue, and incoming data from an event hub. You want to develop a reusable service that can process your temperature data from all these sources. When designing a service such as this with traditional enterprise architecture strategies, you would need to consider server infrastructure and maintenance upfront, scope out necessary hardware, plan to install it, coordinate with IT to manage it, and so on. An alternative to all that work is serverless computing. With serverless computing, your cloud provider manages the provisioning and maintenance of the infrastructure, letting you focus completely on building the app logic. Azure Functions is a key component of this serverless computing offering from Azure and enables you to run pieces of code or functions written in the programming language of your choice in the cloud. In this lesson, you will decide if serverless computing is right for your business needs. Create an Azure Function app in the Azure portal and execute a function using triggers. To help decide whether serverless computing is right for you, let's first learn what serverless is all about. Serverless compute can be thought of as a function as a service, or FaaS, or a microservice that is hosted on a cloud platform. Your business logic runs as functions and you don't have to manually provision or scale infrastructure. The cloud provider manages infrastructure. Your app is automatically scaled out or down depending on load. Microsoft Azure has several ways to build this sort of architecture. The two most common approaches are Azure Logic Apps and Azure Functions, which we focus on in this lesson. Azure Functions is a serverless application platform. It allows developers to host business logic that can be executed without provisioning infrastructure. Functions provides intrinsic scalability and you are charged only for the resources used. You can write your function code in the language of your choice, including C#, F#, JavaScript, Python, and PowerShell Core. Support for package managers like NuGet and NPM is also included, so you can use popular libraries in your business logic. Serverless compute is a great option for hosting business logic code in the cloud. With serverless offerings such as Azure Functions, you can write your business logic in the language of your choice. You get automatic scaling. You have no servers to manage and you are charged based on what is used, not on reserved time. There are some additional characteristics of a serverless solution for you to consider. Suppose you've provisioned VM servers and configured them with enough resources to handle your peak load times. When the load is light, you are potentially paying for infrastructure you're not using. Serverless computing helps solve the allocation problem by scaling up or down automatically, and you're only billed when your function is processing work. Stateless functions are great candidates for serverless compute. Function instances are created and destroyed on demand. If state is required, it can be stored in an associated storage service. Functions are event-driven. This means they run only in response to an event, called a trigger, such as receiving a HTTP request or a message being added to a queue. You configure a trigger as part of the function definition. This approach simplifies your code by allowing you to declare where the data comes from. For example, a trigger or an input binding and where it goes. For example, an output binding. You don't need to write code to watch queues, blobs, hubs, and so on. You can focus purely on the business logic. Functions are a key component of serverless computing, but they are also a general compute platform for executing any type of code. Should the needs of your app change, you can take your project and deploy it in a non-serverless environment, which gives you the flexibility to manage scaling, run on virtual networks, and even completely isolate your functions. Serverless compute will not always be the appropriate solution to hosting your business logic. Here are a few characteristics of functions that may affect your decision to host your services in serverless compute. By default, functions have a timeout of 5 minutes. This timeout is configurable to a maximum of 10 minutes. If your function requires more than 10 minutes to execute, you can host it on a VM. Additionally, if your service is initiated through a HTTP request and you expect that value as a HTTP response, the timeout is further restricted to 2.5 minutes. Finally, there's also an option called durable functions that allows you to orchestrate the execution of multiple functions without any timeout. The second characteristic is execution frequency. If you expect your function to be executed continuously by multiple clients, it will be prudent to estimate the usage and calculate the cost of using functions accordingly. It might be cheaper to host your service on a VM. While scaling, only one function app instance can be created every 10 seconds, for up to 200 total instances. Keep in mind each instance can service multiple concurrent executions, so there is no set limit on how much traffic a single instance can handle. Different types of triggers have different scaling requirements, so research your choice of trigger and investigate its limits. Azure provides several pre-made function templates for common scenarios, quick start and custom functions. When adding your first function, you are presented with the Add Function pane. In the Add Function page, you can choose the trigger for your function. Based on your selections, Azure will generate the function code and configuration with some sample code provided to display the input data received in the log. Selecting a template from the Add Function pane provides easy access to the most common templates. Azure provides over 30 additional templates you can start with. These can be selected from the template list when creating subsequent functions. When you create a function from a template, several files are created. For example, if you opted to use the webhook plus API quick start using JavaScript, the files generated would be a configuration file, function.json, and a source code file, index.js. The functions you create in a function app appear by selecting functions under the functions category in the left menu pane of your function app. When you select a function in your function app, your function pane appears. To display and edit your code for your function, in the left menu pane under Developer, select Code plus Test. In the functions path above the code box, select function.json from the drop-down list and then select test/run from the top menu bar for the input/output pane to appear. There's a pane on the right that includes tabs for input and output. Selecting the Input tab provides parameters to test the HTTP request for your function. After you've created a function, you'll want to test it. There are a couple of approaches: manual execution and testing from within the Azure portal itself. You can start a function by manually triggering the configured trigger. If you are using a HTTP trigger, you can use a tool such as Postman or curl to initiate a HTTP request to your function endpoint URL, which is available from the HTTP trigger definition, get function URL. The portal also provides a convenient way to test your functions. As previously described, after selecting test/run from the top menu bar on the right side of the code box, a tabbed input/output pane appears. Here you can provide parameters to test the HTTP request. When you select Run in this pane, the results appear in the Output tab, along with the status code in the Logs pane. The ability to monitor your functions is critical during development and in production. The Azure portal provides a monitoring dashboard if you turn on the Application Insights integration. In the left menu pane of your function app, under Monitoring, select Logs and open Application Insights. This Application Insights dashboard provides a quick way to view the history of function executions and displays the timestamp, result code, duration, and operation ID populated by Application Insights. You're also able to add logging statements to your function for debugging in the Azure portal. The called methods for each language are passed a logging object, which may be used to log information to the Logs pane located at the bottom of the code window in the Code plus Test pane after running a test. You can log a message using the context.log method. The context object is passed to the handler. We could do the same thing in C# using the log.info method. In this case, the log object is passed to the C# method processing the function. In PowerShell, use write host to write to the log. You can locate the errors and warnings in the Logs pane as well. This pane shows compilation errors and warnings within your code. You've learned how to use Azure Functions to host business logic services in the cloud. It's a great way to add hosted services to your solution that can scale and grow with your business. You focus on the code using the language of your choice, and Azure manages the infrastructure. Functions can integrate with other services like GitHub and Logic apps to create complex and robust serverless workflows quickly and easily. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this module. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. An Azure Functions app doesn't do work until something tells it to execute. For example, we could create an Azure function to send out a reminder text message to our customers before an appointment. If we don't tell the function when it should run, our customers will never receive a message. Now you will examine triggers at a high level and explore the most common types of triggers. But first, let's look at what exactly is a trigger. A trigger is an object that defines how an Azure function is invoked. For example, if you want a function to execute every 10 minutes, you could use a timer trigger. Every function must have exactly one trigger associated with it. If you want to execute a piece of logic that runs under multiple conditions, you need to create multiple functions that share the same core function code. Azure Functions support a wide range of trigger types. Here are some of the most common types. Timer, which executes a function at a set interval. HTTP, which executes a function when a HTTP request is received. Blob, which executes a function when a file is uploaded or updated in Azure Blob Storage. Queue, which executes a function when a message is added to an Azure Storage queue. Azure Cosmos DB, which executes a function when a document changes in a collection. Event Hub, which executes a function when an event hub receives a new event. In this lesson, we're going to focus on the timer, HTTP, and blob trigger types. Now that we have introduced triggers, let's take a look at bindings. A binding is a connection to data within your function. Bindings are optional and come in the form of input and output bindings. An input binding is the data that your function receives. An output binding is the data that your function sends. Unlike a trigger, a function can have multiple input and output bindings. Next, we'll explore how to create a function on a schedule using a timer trigger. It's common to execute a piece of logic at a set interval. Imagine you're a blog owner and you notice that your subscribers aren't reading your most recent posts. You decide that the best action is to send an email once a week to remind them to check your blog. You implement this logic using an Azure Function app with a timer trigger to invoke your function weekly. A timer trigger is a trigger that executes a function at a consistent interval. To create a timer trigger, you need to supply two pieces of information. A timestamp parameter name, which is simply an identifier to access the triggering code. A schedule, which is a cron expression that sets the interval for the timer. Let's look at cron expressions now. A cron expression is a string that consists of 6 fields that represent a set of times. The order of the 6 fields in Azure is second, minute, hour, day, month, and day of the week. For example, you could create a cron expression to create a trigger that executes every 5 minutes. To build a cron expression, you need to have a basic understanding of some of the special characters. Let's take a look at them now. An asterisk selects every value in a field. For example, an asterisk in the day of the week field means every day. A comma separates items in a list. For example, 1, 3 in the field of the week field means just Mondays, day 1, and Wednesdays, day 3. A hyphen specifies a range. For example, 10-12 in the hour field means a range that includes the hours 10, 11, and 12. Finally, a slash specifies an increment. For example, */10 in the minutes field means an increment of every 10 minutes. Let's revisit our example of a cron expression to create a trigger that executes every 5 minutes. There are 6 fields that we have to pay attention to. The first field represents seconds. This field supports the values 0 to 59. Because the field contains a 0, it selects the first possible value, which is 1 second. The second field represents minutes. The value */5 contains 2 special characters. First, the asterisk, which means select every value within the field. Because this field represents minutes, the possible values are 0 to 59. The second special character is the slash, which represents an increment. When you combine these characters together, it means for all values 0 to 59, select every 5th value. An easier way to say that is simply every 5 minutes. The remaining 4 fields represent the hour, day, month, and weekday of the week. An asterisk for these fields means to select every possible value. By placing an asterisk for each of these fields, we select every hour of every day of every month. When you put all the fields together, the expression is read as the first second of every 5th minute of every hour of every day of every month. You can create a timer trigger in the Azure portal. In your Azure Function app, select Timer Trigger from the list of trigger templates. Enter the logic that you want to execute. Supply a timestamp parameter name and the cron expression. In this lesson, we'll focus on creating triggers in the Azure portal, but you can also create triggers programmatically using Core Tools, Visual Studio, or Visual Studio Code. A timer trigger invokes an Azure Function app on a consistent schedule. To define the schedule for a timer trigger, we build a cron expression, which is a string that represents a set of times. An Azure function only runs when something explicitly tells it to execute. In this module, we explored the timer, HTTP, and blob triggers. These are 3 common triggers you can use to launch your functions. Azure Functions include a wide selection of triggers that can be used to respond to other types of input, including external web services and internal Azure services. Although each trigger type has specific requirements, the implementation and usage patterns are similar. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this module. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. Hello and welcome. In this lesson, you will learn how to chain Azure Functions together using input and output bindings. The power of Azure Functions comes mainly from the integrations that it offers with a range of data sources and services, which are defined with bindings. With bindings, developers interact with other data sources and services without worrying about how the data flows to and from their function. Suppose you run a social networking site for professionals. You're allowing your users to upload their headshot images to be posted on their profile. To reduce the workload on the web server, you want to create a serverless backend using Azure Functions to process this data. You want to create an image thumbnail and then save it to permanent storage. In this lesson, you will explore the types of data sources that can be accessed through bindings, read data from Azure Cosmos DB by using Azure Functions, store data in Azure Cosmos DB by using Azure Functions, and send messages to Azure Queue Storage by using Azure Functions. Accessing and processing data are key tasks in many software solutions. Consider some of these scenarios. You've been asked to implement a way to move incoming data from Azure Blob Storage to Azure Cosmos DB. You want to post incoming messages to a queue for processing by another component in your enterprise. Your service needs to grab gamer scores from a queue and update an online scoreboard. All of these examples are about moving data. The data source and destinations differ from scenario to scenario, but the pattern is similar. You connect to a data source and you read and write data. Azure Functions helps you integrate with data and services by using bindings. In Azure Functions, bindings provide a declarative way to connect to your data from within your code. They make it easier to integrate with data streams consistently in a function. You can have multiple bindings providing access to different data elements. This is powerful because you can connect to your data sources without having to code specific connection logic like database connections or web API interfaces. There are two kinds of bindings you can use with functions. Input binding, which connects to a data source. Our function can read data from these inputs. Output binding, which connects to a data destination. Our function can write data to these destinations. There are also triggers, which are special types of input bindings that cause a function to run. For example, an Azure Event Grid notification can be configured as a trigger. When an event occurs, the function will run. The type of binding defines where we are reading or sending data. There is a binding to respond to web requests and a large selection of bindings to interact directly with various Azure services as well as third-party services. A binding type can be used as an input, an output, or both. For example, a function can write to a blob storage output binding, but a blob storage update could trigger another function. Some common binding types include blob storage, Azure Service Bus Queues, Azure Cosmos DB, Azure Event Hubs, external files, external tables, and HTTP endpoints. These types are just a sample. There are more, plus functions have an extensibility model to add more bindings. For further information, read Azure Functions, Triggers and Bindings concepts on the Microsoft website. There is a link to this resource from the additional readings at the end of this lesson. There are 3 properties required in all bindings. However, you may have to supply additional properties based on the type of binding and storage you are using. Let's take a look at them now. Name. This defines the function parameter through which you access the data. For example, in a queue input binding, this is the name of the function parameter that receives the queue message content. Type. This identifies the type of binding. For example, the type of data or service we want to interact with. Direction. This indicates the direction data is flowing. For example, is it an input or output binding? Additionally, most binding types also need a 4th property, connection. This provides the name of an app setting key that contains the connection string. Bindings use connection strings stored in app settings to keep secrets out of the function code. This makes your code more configurable and secure. Bindings are defined in JSON. A binding is configured in your function's configuration file, which is named function.json and lives in the same folder as your function code. For example, let's examine a sample input binding. To create this binding, we first create a binding in our function.json file. Then provide the value for the name variable, for example, a variable that holds the blob data. Next, provide the storage type, for example, blob storage. You then provide the path, which specifies the container and the item name that goes in it. The path property is required when using the blob trigger and should be provided in the format with curly braces around the file name portion of the path. This creates a binding expression that allows you to reference the blob's name in other bindings and in your function's code. For example, a parameter on the function named file name will be populated with the file name of the blob that triggered the function. Next, provide the connection string setting name as defined in the application settings file. This is used as a key to find the connection string to connect to your storage account. Finally, you need to define the direction value as in, as this binding will read data from the blob. Bindings are used to connect to data in your function. In this example scenario, we used an input binding to connect user images to be processed by our function as thumbnails. To connect to a data source, you have to configure an input binding. This binding makes it possible to write minimal code to create a message. You don't have to write code for tasks such as opening a storage connection. The Azure Functions runtime and binding take care of those tasks for you. There are multiple types of input. However, not all types support both input and output. You'll use them whenever you want to ingest data of that type. Here we'll look at the types that support input bindings and when to use them. Here are some of the most common types. Azure Blob Storage bindings allow you to read from a blob. The Azure Cosmos DB input binding uses the SQL API to retrieve one or more Azure Cosmos DB documents and passes them to the input parameter of the function. The document ID or query parameters can be determined based on the trigger that invokes the function. The Mobile Apps input binding loads a record from a mobile table endpoint and passes it into your function. You can read data and work with Azure Table Storage. A full listing of supported bindings is available from the Microsoft website. There is a link to this web page from the additional readings at the end of this lesson. To create a binding as an input, you must define the direction value as in. This is placed inside the binding expressions code in the function.json file. It's also worth noting that the parameters for each type of binding may vary. A binding expression is specialized text in function.json, function parameters, or code that is evaluated when the function is invoked to yield a value. For example, if you have a service bus queue binding, you could use a binding expression to get the name of the queue from app settings. There are a number of types of binding expressions, including app settings, trigger file name, trigger metadata, JSON payloads, new GeoID, and current date and time. Most expressions are identified by being wrapped in curly braces. However, app setting binding expressions are wrapped in % signs rather than curly braces. For example, if the blob output binding path is %symbol environment %symbol /new blob.txt and the environment app setting value is development, a blob will be created in the development container. Input bindings allow you to connect your function to a data source. You can connect to several types of data sources and the parameters for each vary. To resolve values from various sources, you can use binding expressions in the function.json file, function parameters, or code. As with input bindings, there are multiple types of output bindings. You'll use them anytime you want to send or store data. However, not all types support both input and output. Here we'll look at the types that support output bindings and when to use them. For blob storage, you can use the blob output binding to write blobs. The Azure Cosmos DB output binding lets you write a new document to an Azure Cosmos DB database using the SQL API. Use the Event Hub's output binding to write events to an event stream. You must have send permission to an Event Hub to write events to it. Use the HTTP output binding to respond to the HTTP request sender. This binding requires a HTTP trigger and allows you to customize the response associated with the trigger's request. This can also be used to connect to webhooks. The Microsoft Graph output bindings allows you to write to files in OneDrive, modify Excel data, and send email through Outlook. The Mobile Apps output binding writes a new record to a mobile apps table. You can send push notifications with Notification Hub's output bindings. Use the Azure Queue Storage and output binding to write messages to a queue. Send emails using SendGrid bindings. Use Azure Service Bus output binding to send queue or topic messages. Use an Azure Table Storage output binding to write to a table in an Azure storage account. Finally, using Twilio, you can send text messages with Twilio. To create a binding as an output, you must define the direction value as out. This is placed inside the binding expressions code in the function.json file. It's worth noting that the parameters for each type of binding may vary. It's possible to apply multiple bindings to a single function. This allows you to define both input and output bindings, and the input and output can even be the same binding type. This module was about integrating data and services into your functions. We started with a quick tour of the binding types that show up when you add them to a function. Then we looked at reading data from an Azure Cosmos DB by using an input binding. Azure Functions takes care of managing connection strings, and we saw how to read data in our code by using the bindings for HTTP and Cosmos DB. Finally, we explored writing data to different sources, such as Azure Cosmos DB and Azure Queue Storage, with the help of output bindings. If you'd like to learn more about serverless integrations like these with visual workflows and little or no custom code, check out Azure Logic Apps from the Microsoft website. There is a link to this page from the additional readings at the end of this lesson. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this module. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. Hello. In this lesson, you will learn how to create a long-running serverless workflow with durable functions. Durable functions are an extension of Azure Functions that enables you to perform long-lasting stateful operations in Microsoft Azure. Azure provides the infrastructure for maintaining state information. You can use durable functions to orchestrate a long-running workflow. Using this approach, you get all the benefits of a serverless hosting model while letting the durable functions framework take care of activity monitoring, synchronization, and runtime concerns. Suppose your company has a manual approval process for project design proposals. You want to automate the process but still involve humans. As a requirement, the workflow solution that you implement needs to be able to orchestrate activities of varying duration and should be cost-effective. Since your business also runs on custom business logic, the solution must be flexible enough to run proprietary code. By the end of this lesson, you'll learn how to orchestrate a long-running workflow as a set of activities using durable functions. In this lesson, you will explore durable functions, design a long-running approval process workflow, and implement a long-running approval process workflow using durable functions. You can use durable functions to implement complex stateful functions in a serverless environment. Let's look at an example scenario. Your company currently follows a manual approval process for project design proposals. The process has multiple steps, and each step in the process can vary in duration. Implementing an automated process in-house is complex and costly. Coordinating each step takes effort. In addition, you must be able to incorporate custom logic into the workflow. In this lesson, you'll learn about the benefits of durable functions. You'll also learn about the different function types and key concepts associated with durable functions. Let's begin with durable functions and how they manage state. Whereas Azure Functions operate in a stateless environment, durable functions can retain state between function calls. This approach enables you to simplify complex stateful executions in a serverless environment. Durable functions scale as needed and provides a cost-effective means of implementing complex workflows in the cloud. Let's explore some benefits of using durable functions. They enable you to write event-driven code. A durable function can wait asynchronously for one or more external events and then perform a series of tasks in response to these events. You can chain functions together. You can implement common patterns such as fan out or fan in, which uses one function to invoke others in parallel and then accumulate the results. You can orchestrate and coordinate functions and specify the order in which functions should execute. The state is managed for you. You don't have to write your own code to save state information for a long-running function. Durable functions allows you to define stateful workflows using an orchestration function. An orchestration function provides the following benefits. You can define the workflows in code. You don't need to write a JSON description or use a workflow design tool. Functions can be called both synchronously and asynchronously. Output from the called functions is saved locally in variables and used in subsequent function calls. Azure checkpoints the progress of a function automatically when the function awaits. Azure may choose to dehydrate the function and save its state while the function waits to preserve resources and reduce costs. When the function starts running again, Azure will rehydrate it and restore its state. You can use 3 durable function types: client, orchestrator, and activity. Let's look at each in a little more detail now. Client functions are the entry point for creating an instance of a durable functions orchestration. They can run in response to an event from many sources, such as a new HTTP request arriving, a message being posted to a message queue, or an event arriving in an event stream. You can write them in any of the supported languages. Orchestrator functions describe how actions are executed and the order in which they are run. You write the orchestration logic in code, C# or JavaScript. Activity functions are the basic units of work in a durable function orchestration. An activity function contains the actual work performed by the tasks being orchestrated. You can use durable functions to implement many common workflow patterns. These patterns include function chaining, fan-out/fan-in, async HTTP APIs, monitor, and human interaction. Let's explore each of these patterns in a little more detail now. In the function chaining pattern, the workflow executes a sequence of functions in a specified order. The output of one function is applied to the input of the next function in the sequence. The output of the final function is used to generate a result. Next is fan-out/fan-in. This pattern runs multiple functions in parallel and then waits for all the functions to finish. The results of the parallel executions can be aggregated or used to compute a final result. The async HTTP APIs pattern addresses the problem of coordinating state of long-running operations with external clients. A HTTP call can trigger the long-running action. Then it can redirect the client to a status endpoint. The client can learn when the operation is finished by polling this endpoint. With Monitor, this pattern implements a recurring process in a workflow, possibly looking for a change in state. For example, you could use this pattern to poll until specific conditions are met. Finally, the human interaction pattern. This combines automated processes that also involve some human interaction. A manual process within an automated process is tricky because people aren't as highly available and as responsive as most computers. Human interaction can be incorporated using timeouts and compensation logic that runs if the human fails to interact correctly within a specified response time. An approval process is an example of a process that involves human interaction. Now we will look at how to design a workflow based on durable functions. You can use durable functions to orchestrate a long-running workflow as a set of activities. You can map each step in the process to a function type and each task to an activity. Having an automated process means you don't have to worry about manually monitoring or escalating a task if it isn't done. As we continue to think about automating our proposal approval process, we need to consider the cases when a step in the process does not complete in time and needs to be escalated. For example, what if we need a manager's approval for a particular size of proposal, but the manager is late with a response? Escalation steps are useful to this business as they move along a task when a deadline has been reached. They ensure tasks are completed and not forgotten. An escalation step could involve sending out reminders or even reassigning a task to someone higher up the managerial hierarchy. Now you'll design an approval process workflow based on durable functions. In the next exercise, you'll apply this knowledge to create an app with Azure Durable Functions. Our workflow begins when a project design is submitted for approval. The proposal is assigned as an approval task to a manager. The manager will either approve or reject the proposal. In the real world, this event would probably generate and send a notification to the proposal author to let them know the outcome of the approve-reject request. In this example, the status of the task would then be changed to either approved or rejected. The workflow steps are as follows. A project design is submitted. An approval task is allocated to a manager so they can review the project design proposal. The project design proposal is rejected or approved. An escalation task is allocated if the approval task isn't completed within a predefined time limit. It's possible to map the workflow steps to the function types used in a durable functions workflow. For example, submitting a project design proposal for approval could map to the client function. Assigning an approval task to a relevant member of staff could map to the orchestration function. The approval task could map to the activity function. And an escalation task could map to the activity function. When you are working with a long-running workflow, it's important to consider some additional scenarios. For example, what should happen if a task isn't completed within an acceptable period of time? How can you check the status of a task? You can address these concerns with timeouts and escalation paths. In the example scenario, you've been asked to amend your new workflow to incorporate an escalation step to take action if a project design proposal isn't approved in a timely fashion. In this lesson, you'll learn how to control long-running tasks using durable timers and how to add an escalation path based on the timer. Durable Functions provides timers for use in the orchestrator functions, which you can use to implement delays or set up timeouts for asynchronous actions. You should use durable timers in orchestrator functions instead of the set timeout and set interval functions. You create a durable timer by calling the createTimer method of the durable orchestration context. This method returns a task that resumes on a specified date and time. Let's look at using timers for delay. For example, using durable timers for delay, which sends a reminder every day for 10 days. In your JavaScript code, it's important to note that you should always use current UTC date time to obtain the current date and time, instead of date.now or date.utc. Let's also explore a scenario where durable timers could be used to set up a timeout and a different path will be executed if a timeout occurs. In this example scenario, the function waits until either the getQuoteActivity function completes or the deadline timer expires. If the activity function completes, the code follows the success case. Otherwise, it follows the timeout case. You can access the full source code for this example from the reading at the end of this lesson. Durable Functions enables you to implement long-running workflows without requiring that you maintain state information manually. Azure provides the infrastructure in which durable functions run. You focus on the logic for the functions that perform the tasks in your workflow. In this lesson, we learned about durable functions and how to orchestrate our simple design proposal approvals process. Using durable timers, we can add an escalation path to our workflows, especially for those long-running indeterminate tasks. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this lesson. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. Hello. In this lesson, you will learn how to develop, test and publish Azure Functions by using Azure Functions core tools. The Azure Functions core tools are command line utilities that enable you to develop and run functions locally and publish them to Azure. Suppose you're a developer for a car dealership chain. The salespeople are always looking for ways to modernize their workflow. Your manager has decided to build a set of applications backed by Azure Functions. The first service he'd like to build involves loan interest calculations. He's asked you to look into creating functions that can be called over the web to run loan interest calculations. You've decided to start by learning how to use the Azure Functions core tools to build and publish a function. In this lesson, you'll use the Azure Functions core tools from the command line to create a new local functions project and function. You'll modify the starter code generated by the core tools to run a simple interest calculation and run the function locally to test it. When it's ready, you'll use the Azure CLI to create a function app in Azure, publish your function, then invoke it over the web. By the end of this lesson, you'll be able to use the Azure Functions core tools to create new functions, projects and functions, run and test functions locally, and publish functions to Azure. This lesson's exercise can be completed in the browser and doesn't require an Azure subscription or local development environment. The Azure Functions core tools let you develop and run functions on your local computer from the command line. You've decided you'd like to try building your first function, the simple interest calculator, by developing it locally on your own computer and not in the Azure portal's functions editor. You aren't sure whether you want to use a development environment like Visual Studio or Visual Studio Code that can be extended to support Azure Functions directly. So you'll use the core tools from the command line and a basic text editor. Now you'll learn how to use the core tools to create and run functions locally. The Azure Functions core tools are a set of command line tools that you can use to develop and test Azure Functions on your local computer. The core tools feature a variety of functions-related capabilities. Their primary purpose is to generate the files and folders you need to develop functions on your local computer, run your functions locally so you can test and debug them, and publish your functions to Azure. The core tools are packaged as a single command line utility. If you run the command func from the command line without any additional commands, it will display the version information and a usage guide. The core tools are standalone utilities, not an extension of a larger integrated development environment or tool. You can accomplish the above tasks with nothing but the command line and the core tools, and use any text editor you like to write code and modify configuration. In practice, you'll also need the Azure CLI or Azure PowerShell to log into Azure and perform other management tasks. Other functions development tools, such as the functions-related features in Visual Studio and the Azure Functions extension for Visual Studio Code, are built on top of the core tools. In other documentation, you may see references to different versions of the core tools. We recommend using the newest available revision as it offers the best support for most scenarios, and it can be installed on Windows, macOS and Linux computers. We'll be discussing and using version 3.x in this lesson, but you won't need to install anything on your own computer to complete it. You'll use the in-browser Cloud Shell environment for development, and the core tools are already installed there, along with the Azure CLI and a code editor. OK, let's now explore local development versus the Azure Portal development. The Azure Portal features a functions editor experience, but in most cases it does not support working with functions that were developed locally. Once you start using a local development workflow based on the core tools, don't expect to be able to use the portal to make changes to your functions. Let's start with core tools by taking a closer look at how to create functions and run them locally. We'll look at how to publish to Azure later. To do this, we begin with how to create functions locally by exploring function apps and functions projects. Every function published to Azure belongs to a function app, which is a collection of functions that are published together into the same environment. All of the functions in an app share a common set of configuration values and must all be built for the same language runtime. Each function app is an Azure resource that can be configured and managed independently. When you develop functions locally, you work within a functions project, a folder that contains the code and configuration files that define your functions. A functions project on your computer is equivalent to a function app in Azure and can contain multiple functions that use the same language runtime. To get started developing, you need to create a functions project folder that's organized correctly. Every new function you add to the project requires additional code and configuration that must be complete and correctly structured, or your functions will not be able to run. If you want to use your own naming conventions and your own code, you could become familiar with the names and contents of the files needed in a functions project folder and create them yourself. However, doing so would be time-consuming and error-prone. You can use the core tools to generate function projects and functions from scratch. Let's take a look at this now. To create a new functions project, run func-init on the command line. Func-init will ask you which language runtime you'd like to use for the app and tailor the project folder's contents appropriately. When you create a new functions project, the files included in the project folder depend on the language runtime you select. Regardless of the runtime you choose, the two most critical project files are always present. These are host.json and local.settings.json. Host.json stores runtime configuration values, such as logging options, for the function app. The settings stored in this file are used both when running functions locally and in Azure. Local.settings.json stores configuration values that only apply to the function app when it is run locally with the core tools. This file contains two kinds of settings: local runtime settings, used to configure the local functions runtime itself, and custom application settings, which you can add and configure based on your app's needs and can be accessed and used by all the functions in the app. It's worth noting that functions projects that the command func-init generates don't have any functions in them. Let's find out how to add one. Each individual function in a project requires code and configuration to define its behavior. Running the new function command in a functions project folder will create a new function and all the files you need to get started developing. After asking you which kind of function trigger you want to use and what you'd like to name your function, the func new command will generate a complete publish-ready starter implementation in your function project's chosen language. For example, choosing option 8 for a HTTP trigger. This will then build a function from the HTTP trigger template. The starter code illustrates how to use the type of trigger you selected and is there to help you get started quickly. Just replace the body of the function with your own implementation and you're ready to build, run, test and publish. In the next part, we'll use the new function command to create a HTTP-triggered function and modify the starter implementation to perform a simple interest calculation. Let's continue with how to run functions locally. Functions aren't programs that can be run on their own. They must be hosted by the functions host. The host is what powers everything outside of your function code. It loads configuration, listens for triggers and HTTP requests, starts the worker process for the language your functions are written in, writes log output, and more. In Azure, function apps run the function host automatically when they start. You can use the core tools to run your own instance of the functions host and try out your functions locally before you publish them. By running your functions before publishing them, you can make sure your configuration and code loads correctly and test out your functions by making real HTTP calls to them without the need for Azure resources. To start the functions host locally, run the command func start from a functions project folder. At the end of the output, the core tools will display local URLs you can use to call each of your functions. While the host is running, you can use any tools or libraries that make HTTP calls, like curl, to interact with your functions. The core tools will write any log output produced by the host to the terminal in real time. You can use the core tools to publish your functions to Azure. Now that you've built and tested your simple interest function, you'd like to get it published to Azure. It would be great to see it up and running on the web and provide the URL to your colleagues so they can see how it can be called from anywhere. Now you'll see how to create a function app in Azure and use the core tools to publish your functions project to it. Before you can use the core tools to publish a project, you need to create a function app in Azure. This is not a capability of the core tools. Creating function apps is one of the responsibilities of the Azure management tools, which include the Azure Portal, Azure CLI, and Azure PowerShell. In the next exercise, you will use the Azure CLI command AZ function app to create a function app to which we can publish our code. Within the scope of this lesson, the most important option to consider when creating a function app is the language runtime. A given function app only supports a single language runtime. If you already have a local functions project you want to publish, make sure to create the function app with the same language runtime. If you try to deploy a project to an app with a different runtime, publishing will halt with an error. OK, let's look at publishing to Azure. To publish a functions project to Azure, run the command func Azure function app publish, then the app name from the functions project folder. It's important to note here that app name is a reference to the name of the target function app in Azure, not the name of your project folder, which can be different. The core tools don't ask you to sign into Azure. Instead, they access your subscriptions and resources by loading your session information from the Azure CLI or Azure PowerShell. If you don't have an active session in one of those tools, publishing will fail. It's possible to publish from the core tools without the Azure CLI or Azure PowerShell, but it's much easier if you do have them. It's recommended you install one or the other and log in before trying to publish. Once the tools indicate that publishing is complete, your functions are up and running in Azure. The final output from the core tools will show the functions that were published, including the invocation URL of each function. Here are a few things to keep in mind when you use the core tools to publish your functions. The core tools do not validate or test your functions code during publishing. Make sure to use func start to do some testing before you publish. When you publish, any functions already present in the target app are stopped and deleted before the contents of your project are deployed. You can't combine functions from multiple projects into one app by publishing them in sequence. All of the functions you want in the app must be in one project. Publishing to Azure does not create any kind of relationship between the local project and the target function app. You can publish a single functions project to multiple function apps. You can also republish a project to the same app repeatedly as you work on your code. The invocation URLs displayed after you publish may include a code parameter in the query string. By default, HTTP functions created by the core tools are configured with an authorization level of function, meaning they require callers to provide a secret key in the request headers or query string. The core tools includes the key in the query string of the displayed URL for your convenience. Let's recap what we learned in this lesson. In this lesson, you use the Azure Functions core tools to get started developing functions from the command line. You created a local functions project and the simple interest function with nothing but the core tools and a text editor and ran the function locally to test it. After using the Azure CLI to create a function app in Azure, you use the core tools to publish your function and interact with it in Azure. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this lesson. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. Hello and welcome. In this lesson, you will learn how to develop, test and publish Azure Functions by using Azure Functions core tools. Serverless architecture makes use of infrastructure provided by the cloud. You don't have to provision, manage, scale and maintain any machinery or networks. Azure Functions is a fully managed PaaS service offered by Microsoft Azure to implement serverless architecture. Azure Functions is a fully scalable, resilient, reliable and secure service. Imagine that you're a senior web developer in a research role for an online luxury watch dealer, building a website based on Azure Web Apps. You've been asked to provide new functionality by writing and deploying individual methods that can be deployed, manually executed, scheduled, or even triggered by other Azure services. The company follows a test-driven development process, so you're also required to write automated unit tests for the new services. You have a team of developers well versed with Microsoft technologies, including the .NET Framework and Visual Studio. You decide to investigate the use of Azure Functions to meet your requirements. By the end of this lesson, you'll be able to build and test an Azure function locally using Visual Studio 2019. You'll then see how to deploy the function to Azure from Visual Studio. In this lesson, you will develop an Azure function in Visual Studio 2019, test and debug an Azure function in Visual Studio 2019, deploy an Azure function directly from Visual Studio 2019 to Azure, and manage Azure Functions code. You can write, debug and deploy an Azure function from within the Azure portal. However, there are many scenarios when writing functions directly in the production staging or test environments might not be suitable. For example, you could be writing automated unit tests for Azure Functions or using on-demand deployment of Azure Functions to Azure Function apps in Azure. Additionally, many developers prefer to use their favorite code editor and development tools rather than the environment provided by the Azure portal. Developing functions with Visual Studio enables you to manage Azure Functions code with code of other services inside the same projects. In the luxury watch online website scenario, the developers are already familiar with Visual Studio. So you decide to use Visual Studio as the primary development environment for creating Azure Functions. Additionally, Visual Studio provides an excellent environment for testing your functions locally before deploying them to Azure. In this lesson, you'll learn about the tools available with Visual Studio for building Azure Functions. To build and test an Azure function locally, you'll see how to install these tools and use them. Let's start by looking at how you can modify the installation of Visual Studio. Upon loading Visual Studio 2019, go to Visual Studio Installer and select Modify. The Modifying Visual Studio page appears. Under the Workloads tab, select the ASP.NET and Web Development and Azure Development boxes, and then select Modify. The Azure Functions tools are a Visual Studio extension that enable you to create, test, and deploy Azure Functions in your local development environment. To quickly create a new Azure Function app, this extension provides a template that you can use. You can then deploy an Azure Function directly to Azure from Visual Studio. The Azure Functions and Web Jobs Tools extension is included in Visual Studio 2019. An Azure Function app hosts one or more Azure Functions. It provides the environment and runtime for the functions. An Azure Function is triggered by an event rather than being called directly from an app. You specify the type of event that will trigger the functions in your Azure Function app. The events available include Service Bus Queue Trigger. Use this trigger to run the function when a new item is added to an Azure Service Bus Queue. A HTTP trigger runs the function when a HTTP request occurs in a web app. You can also use this trigger to respond to webhooks. A webhook is a callback that occurs when an item hosted by a website is modified. For example, you can create an Azure function that is fired by a webhook from a GitHub repository when an item in the repository changes. Timer trigger. Use this event to run the Azure function at regular intervals following a schedule that you define. Queue trigger. This trigger fires the function when a new item is added to an Azure storage queue. Blob trigger. This type of function runs when a file is uploaded or modified in Azure Blob Storage. An event hub trigger runs the function when an event hub receives a message. Service bus topic trigger. This trigger runs the function in response to a new message arriving on a service bus topic. And Azure Cosmos DB trigger. This trigger runs when a document is added to or modified in an Azure Cosmos DB database. You can use this trigger to integrate Azure Cosmos DB with other services. For example, if a document representing a customer's order is added to a database, you could use a trigger to send a copy of the order to a queue for processing. An Azure Function app stores management information, code, and logs in Azure Storage. Create a storage account to hold this data. The storage account must support Azure Blob, Queue, Files, and Table storage. Use a general Azure Storage account for this purpose. You specify which storage account to use for the function using the dialog box. An Azure function can perform privileged or sensitive operations. An Azure function triggered by a HTTP request could be exposed publicly. You might need to limit the ability to run this function to selected groups of users. You protect an Azure function by specifying the access rights required to trigger the function. Anonymous. No authentication is required and any user can trigger the function. Function. The HTTP request must provide a key that enables the Azure function runtime to authorize the request. You create this key separately and you can maintain it using the Azure portal. Admin. This is similar to function, as the user must specify a key with the HTTP request that triggers the function. The difference is that the key is an admin key and can be used to access any function in the function app. As with a function key, you create this key separately. If you're creating a function triggered by events other than HTTP requests, you're required to provide a connection string and other details necessary for the function app to access the resource triggering the event. For example, if you're writing a function triggered by a blob storage event, you must specify the connection string for the corresponding blob storage account. Okay, let's now take a look at the structure of an Azure function. An Azure function is implemented as a static class. The class provides a static asynchronous method named run, which acts as the entry point for the class. For example, code generated by Visual Studio examines the query string provided as part of the URL for the request and looks for a parameter called name. The code also uses a stream reader to deserialize the body of the request and attempts to read the value of a property also called name from the request. If name is found either in the query string or the body of the request, it's returned in the response. Otherwise, the function generates an error response with the message, "Please pass a name on the query string or the request body." The function returns a value containing any output data and results wrapped in an iActionResult object. The value is returned in the body of the HTTP response for the request. Different types of trigger receive different input parameters and return types. For example, the code generated for a blob trigger. The contents of the blob is made accessible through a stream object, and the name of the blob is also provided. No data is returned by the trigger. Its purpose is to read and process the data in the named blob. In all cases, an Azure function is passed an iLogger parameter. The function can use this parameter to write log messages, which the function app will write to storage for later analysis. An Azure function also contains metadata that specify the type of the trigger and any other specific information and security requirements. You can modify this metadata using the HTTP trigger, blob trigger, or other trigger attributes. The function name attribute that precedes the function is an identifier for the function used by the function app. This name doesn't have to be the same as the name of the function, but it's good practice to keep them synchronized to avoid confusion. You can use the visual debugger to build and test the Azure function app locally. Press F5 or on the debug menu, select Start Debugging. The local version of the function runtime will start. Your functions will be available for testing. For example, showing the runtime hosting of a function where the function is triggered by a HTTP event. The URL indicates the endpoint to which the function is currently attached. If you open a web browser and visit this URL, you'll trigger the function. For example, the response generated by a HTTP GET request that doesn't include a body. The message generated by the code returns the bad request object result object from the function. If you provide a query string that includes a name parameter, the value is read and processed by the function. An Azure function runs in the cloud in the context of an Azure Functions app. A function app is a container that specifies the operating system for running an Azure function, together with the resources available, such as the memory, computing power, and disk space. The Azure Functions app also provides the public URL for running your functions. Behind the scenes, an Azure Functions app is a collection of one or more virtual machines, or VMs, running a web server. When you publish an Azure function, you deploy it to these VMs. In the Luxury Watch online website scenario, you'll deploy the Azure functions you create to the cloud. You need to create an Azure Functions app and then publish your functions to this app. You want to determine the best way to do this. There are several options available for publishing an Azure function. In this lesson, you'll learn about some of these options, such as deployment from Visual Studio, continuous deployment, and zip deployment. Let's look at each in a little more detail now. Azure Functions tools for Visual Studio enable you to deploy an Azure function directly from Visual Studio. The Azure Functions template provides a publish wizard. Using this wizard, you connect to your Azure account and either specify an existing Azure Functions app or create a new one. The functions in your project are rebuilt and then deployed to the Azure Functions app. The Publish wizard requires that you either have access to the Azure Functions app that will host your functions, or you have an Azure subscription that you can use to create an Azure Functions app as part of the publication process. You'll investigate the Publish wizard in more detail in the exercise that follows this lesson. Deployment from Visual Studio is a great feature for developers. If developers have access to an Azure subscription, they can create an Azure Functions app and publish code to Azure to perform testing in an environment that is similar to a production environment. Once a function is stable, it can be deployed to an Azure Functions app, providing the production environment. Azure Functions makes it easy to deploy your function app using App Service Continuous Integration. Azure Functions integrates with many deployment sources with the following currently supported: Bitbucket, Dropbox, External Repository, Git or Mercurial, Git Local Repository, GitHub, OneDrive, and Azure DevOps. This enables a workflow where function code updates made by using one of these integrated services triggers deployment to Azure. Continuous deployment is a great option for projects where multiple and frequent contributions are being integrated. It also lets you maintain source control on your functions code. You can configure continuous deployment from the Azure portal using the Deployment Center feature of an Azure Functions app. Deployment is configured on a per-function app basis. Azure Functions can be deployed from a zip file using the push deployment technique. You can do this with the Azure CLI or by using the REST interface. The zip file contains the executable code for your functions. Zip deployment copies these files to the www root folder in the function app. You can perform zip deployment using the function app deployment command in the Azure CLI. In this module, you learned about Azure Functions. You've seen how to use Visual Studio to create an Azure function and deploy it to the cloud. You've also seen how to create and run unit tests for an Azure function. In this lesson, you use the Azure Functions core tools to get started developing functions from the command line. You created a local functions project and the simple interest function with nothing but the core tools and a text editor and ran the function locally to test it. After using the Azure CLI to create a function app in Azure, you use the core tools to publish your function and interact with it in Azure. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this lesson. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. Hello and welcome to this lesson, where you will learn how to create a function triggered by a webhook. Webhooks offer a lightweight mechanism for apps to be notified by another service when something of interest happens via a HTTP endpoint. You can use a webhook to trigger an Azure function and then analyze the message to determine what happened and how to respond. Suppose you are a developer in an IT department. Management wants a regular report on updates to the company's technology wiki. They'd like to know who contributes and how often it's updated and what pages are updated most often. The wiki is hosted on GitHub as a GitHub wiki on one of the company's Git repositories. You've heard that GitHub supports webhooks and you can receive notifications for all kinds of events. You are also familiar with Azure Functions and decide to use a function as the listener for wiki update events. You are also familiar with Azure Functions and decide to use a function as the listener for wiki update events. By the end of this lesson, you'll learn how to create a function triggered by a webhook and how to secure a webhook message or payload with a secret. In this lesson, you will trigger your function with a webhook, analyze the message from the webhook, and secure webhook payloads with a secret. Now we'll look at how to create a function that is triggered by a webhook. You've decided on using Azure Functions to monitor the company GitHub wiki for updates. Each time the wiki is updated, you want to be able to trigger a function that can process details about the update, such as updated date, contributor name, and so on. The first step is to create an Azure Function app that contains a function triggered by a webhook. In this lesson, you'll learn about the benefits of using webhooks and how you can trigger an Azure function using webhooks. Webhooks are user-defined HTTP callbacks. They're triggered by some event, such as pushing code to a repo or updating a wiki page. When the event occurs, the source site makes a HTTP request to the URL configured for the webhook. With Azure Functions, we can define logic in a function that can be run when a webhook message is received. One common use of webhooks in a DevOps environment is to notify an Azure function that the code or configuration for an application has changed in a GitHub. The payload of the message sent through the webhook contains the details of the event. You can use the webhook with a function to perform a task such as deploying the updated version of the application. Azure Functions is a serverless compute service. It enables you to run code without having to explicitly provision or manage any infrastructure. You can use Azure Functions to run script or code in response to a variety of events. Now let's look at triggers and bindings. A trigger causes a function to run. A trigger defines how a function is invoked. A function must have exactly one trigger. Triggers have associated data, which is often provided as the payload of the function. A binding is used to connect a resource to a function. You can define input bindings and output bindings. Data from a binding is provided to the function as parameters. For example, you can connect a database to your Azure Functions code by using a binding. Then you don't need to wire up the database to the function with any connection code. Bindings are optional, and a function might have one or multiple input and/or output bindings. Now we'll look at how to set up a webhook for a GitHub repository. In GitHub, webhooks can be set up on an organization or a specific repository. The webhook will be triggered each time one or more subscribed events occurs. For example, the Golem event allows you to listen for wiki updates, specifically creation and updates for a wiki page. Now you'll learn how to set up a webhook listening for a change event from your company's GitHub wiki. Setting up a webhook is a two-step process. First, you specify how you want your webhook to behave through GitHub and what events it should listen to. Then, you set up your function in Azure Functions to receive and manage the payload received from the webhook. In GitHub, you can install webhooks for an organization or a repository. In the example scenario case, we're setting up a webhook on a specific repository. To set up the webhook, go to the settings page of your repository in the GitHub portal. Select Webhooks and then select Add Webhook. Alternatively, you can build and manage a webhook through the Webhooks API, but we will not cover this approach in this lesson. Webhooks require a couple of configuration options before you can use them. We'll go through each of these settings next. The payload URL is the URL of the server that will receive the webhook post requests. Each event type has a specific payload format. That payload contains information about the event that triggered the webhook. Webhooks can be delivered using two different content types. The application/JSON content type delivers the JSON payload directly as the body of the post request. And the application/x-www-form-URL encoded content type sends the JSON payload as a form parameter called payload. You should note that the Add Webhook page also enables you to specify how to protect the information sent by the webhook by using a secret. This topic is covered later in this module. Now let's turn to events. Events are at the center of webhooks. Events occur whenever actions are taken in the repository. When the event occurs, the webhook fires off and calls the URL that you specify, sending along the payload and event information to your URL. A full list of webhook events and when they can run can be found in the webhooks events reference. For example, to respond whenever an issue is raised in a repository, click Let me select individual events and then select Issues. Make sure you select Active to receive issue events for triggered webhooks. To listen for updates to the wiki for the repository, select the Wiki checkbox. This event is the Golem event mentioned earlier. In the next exercise, we'll walk you through the process of setting up a webhook for a GitHub repository. The GitHub Golem event enables you to listen for wiki updates. When this event occurs and our Azure Functions function is triggered, you can parse the payload to retrieve and process the data sent. You've shown the IT department that you can listen for Golem events on your company's GitHub repository by setting up a webhook in GitHub. You've also demonstrated how Azure Functions enables you to run code when the function receives a webhook request. Now, we'll examine the payload from the Golem event so we can update our function to parse it correctly. The payload for the Golem event contains the following items. Pages. With the pages that were updated, each page includes the following information. Page_name has the name of the page. Title contains the current page title. Action is the action that was performed on the page. It can be created or edited. And HTML_URL is the HTML wiki page. Then you'll have repository with information about the repository containing the wiki page, including name for the name of the repository, owner containing the details of the owner of the repository, and HTML_URL with the address of the repository. Then you'll have sender with information about the user that raised the event that caused the webhook to fire. This information is passed as the body of a HTTP post request. We'll need to update our function logic to be able to parse and process this information correctly. Recall that the webhook runs when a specific event occurs. The webhook then sends a request to the URL on which your Azure Functions code is set up to listen, using the URL for your function. The payload is passed to the Azure function. Your function can parse the request body to extract the fields from the payload and take the appropriate actions. You can retrieve the repository name from the payload. The event type is available in the x-github-event request header. This data is output in a function response. In the next exercise, we'll update our function code to be able to handle incoming Golem events correctly. Once your function is configured to receive payloads, it will listen for any payloads sent to the endpoint you configured. For security reasons, you might want to limit requests to those coming from GitHub. There are a few ways to go about this. For example, you could opt to approve requests from GitHub's IP address. An easier method is to set up a secret token and validate the request using this token. In the example scenario, your IT department's management are happy with the webhook triggered function that you've created in an Azure Functions app. All of the information regarding updates to the company wiki are being parsed by that function and sent to the business each time the Golem event is triggered. The management has asked how secure the information passed from GitHub is. They've asked you to find a way to secure the information and verify it's GitHub that is sending updates. Now you'll learn how to secure your webhook payload with a secret and validate payloads from GitHub. Setting a webhook secret allows you to ensure that post requests sent to the payload URL are from GitHub. When you set a secret, you'll receive the x-hub-signature header in the webhook post request. In GitHub, you can set the secret field by going to the repository where you have set up your webhook and then editing the webhook. We'll show you how to do that for our example in the next exercise. When your secret token is set, GitHub uses it to create a hash signature for each payload. This hash signature is passed along with each request in the headers as x-hub-signature. When your function receives a request, you need to compute the hash using your secret and ensure that it matches the hash in the request header. GitHub uses a HMAC SHA-1 hex digest to compute the hash, so you must calculate your hash in this same way using the key of your secret and your payload body. The hash signature starts with the text SHA-1 equals. In this module, you learned about the benefits of webhooks. You learned how to create a function in Azure Functions triggered by a webhook. You saw how to set up a webhook for a GitHub repository and how to trigger your function with a GitHub event. Finally, you learned how to protect your function using a secret. Now finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this module. And when you're working your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. And if you created a new GitHub repository for your wiki, you can now delete it. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. Hello and welcome to this lesson, where you will enable automatic updates in a web application using Azure Functions and SignalR service. Consider the following scenario. Your company is planning to launch a new website that provides stock price information to customers. Recently, an intern created a website prototype for the new application, and the lead architect has now asked you to step in and improve the solution. Your objective is to update the app to implement automatic updates of the stock price information, but ensure communication between the client and server happens only when data changes on the server. In this lesson, you will implement a function in Azure Functions that runs only when data changes in an Azure Cosmos DB. Implement a function in Azure Functions to broadcast changes to connected clients using SignalR service. Update the client web application to respond to SignalR messages, and modify a Vue.js and JavaScript web application to use SignalR. The application's current architecture reports stock information by fetching changes from the server based on a timer. This design is often called a polling-based design. Before we analyse any limitations, let's review the current architecture. The server is responsible for storing stock information, and the client renders data in the browser. We'll set up the current solution on your local machine later. First, we'll look at the server side. The stock price information is stored on the server in an Azure Cosmos DB database. When triggered by a HTTP request, the function uses bindings to return content from the database. The function named getStocks is responsible for reading the stock information from the database. As mentioned, the connection to the Azure Cosmos DB database is achieved by using an input binding. This binding is configured in the function .json file. The type property defines the function as a HTTP triggered function. The auth level and direction properties allow unauthenticated incoming requests. The name property exposes the request context through a parameter named rec. And the methods property accepts GET requests. The second HTTP binding defines what is returned from the function. The type and direction properties allow the function to return a HTTP response, and the name property exposes the response context through a parameter named res. The third binding establishes a connection to Azure Cosmos DB. The type and direction properties make an Azure Cosmos DB data available as the function is called. The name property exposes the data to the function through a parameter named stocks. The connection string setting property connects to the Azure Cosmos DB data with a connection string. The database name property points to the stocks DB database, and the collection name property points to the stocks data collection. With these bindings, GET sends a request to getStocks to make data available through the stocks parameter. The function code to retrieve stock information is trivial thanks to the power of Azure Functions bindings. The sample client uses Vue.js to compose the user interface and the Axios HTTP client to handle requests to the function. The page uses a timer to send a request to the server every 5 seconds to request stocks. The response returns an array of stocks, which are then displayed to the user. The update method is called every 5 seconds once polling is started by the startPoll method. Inside the update method, a GET request is sent to the getStocks function and the result is set to app.stocks, which updates the UI. The server and client code is relatively straightforward, but as we'll see, this simplicity brings with it some limitations. In the local.settings JSON file, the host section includes the following settings: host, local HTTP port as 7071, CORS as localhost:8080, and CORS credentials as true. This configuration allows a web application running at localhost:8080 to make requests to the function app running at localhost:7071. The property CORS credentials tells function app to accept credential cookies from the request. CORS is a HTTP feature that enables a web application running under one domain to access resources in another domain. Web browsers implement a security restriction known as same-origin policy that prevents a web page from calling APIs in a different domain. CORS provides a secure way to allow one domain, the origin domain, to call APIs in another domain. You can set CORS rules individually for each of the Azure storage services by calling set blob service properties, set file service properties, set queue service properties, and set table service properties. Once you set the CORS rules for the service, then a properly authorized request made against the service from a different domain will be evaluated to determine whether it is allowed according to the rules you have specified. Now let's think about some of the drawbacks of this timer-based polling approach. In the timer-based polling prototype, the client application contacts the server whether or not changes exist to the underlying data. Once data is returned from the server, the entire list of stocks is updated on the web page, again, regardless of any changes in the data. This polling mechanism is an inefficient solution. Selecting the best polling interval for your scenario is also a challenge. Polling forces you to make a choice between how much each call to the backend costs and how quickly you want your app to respond to new data. Delays also often exist between when new data becomes available and when it's detected by the app. In the worst case, the potential delay for detecting new data is equal to the polling interval. So why not use a smaller interval? As the application scales, the amount of data exchanged between the client and server will become a problem. Each HTTP request header includes hundreds of bytes of data along with the session's cookie. All this overhead, especially when under heavy load, creates wasted resources and unnecessarily taxes the server. Now that you're more familiar with the starting point of the application, it's time to get the application running on your machine. Next, we'll move away from polling and toward an app that pushes data updates as they occur to connected clients. This new design reduces traffic and makes a more efficient UI by only updating as data changes. The three technologies that we'll use to deliver this updated solution are Azure Cosmos DB, Azure Functions, and SignalR. As data changes in the database, Azure Cosmos DB exposes a change feed. The change feed support in Azure Cosmos DB works by listening to a database container for changes. It then outputs the sorted list of change documents in the order in which they were modified. By listening to the change feed, your application can automatically respond to data changes. The key difference between this function and the original getStocks function is that the function is now triggered based on changes to our data. In the preceding exercise, we triggered our function based on requests from the client and pulled back all data through an Azure Cosmos DB input binding. Using the Azure Cosmos DB trigger automatically makes our data retrieval more efficient. Azure Functions features a binding that runs code anytime data is updated in an Azure Cosmos DB change feed. Once a function is listening to the change feed, then you can work with a subset of your data that just represents data changes. When paired with a persistent connection to the client, the function can contact individual clients on demand, which is the foundation for a real-time application architecture. In contrast to polling, a more favorable design features persistent connections between the client and server. Establishing a persistent connection allows the server to push data to the client at will. The on-demand nature of the connection reduces network traffic and load on the server. SignalR allows you to easily add this type of architecture to your application. SignalR is an abstraction for a series of technologies that allows your app to enjoy two-way communication between the client and server. SignalR handles connection management automatically. It lets you broadcast messages to all connected clients simultaneously, like a chat room. You can also send messages to specific clients. The connection between the client and server is persistent, unlike a classic HTTP connection, which is re-established for each communication. A key benefit of the abstraction provided by SignalR is the way it supports transport fallbacks. A transport is a method of communicating between the client and server. SignalR connections begin with a standard HTTP request. As the server evaluates the connection, the most appropriate communication method or transport is selected. Transports are chosen depending on the APIs available on the client. For clients that support HTML5, the WebSockets API transport is used by default. If the client doesn't support WebSockets, then SignalR falls back to server-sent events, also known as event source. For older clients, AJAX long polling or forever frame is used to mimic a two-way connection. The abstraction layer offered by SignalR provides two benefits to your application. The first advantage is future-proofing your app. As the web evolves and APIs superior to WebSockets become available, your application doesn't need to change. You could update to a version of SignalR that supports any new APIs and your application code won't need an overhaul. The second benefit is that SignalR allows your application to gracefully degrade depending on supported technologies of the client. If it doesn't support WebSockets, then server-sent events are used. If the client can't handle server-sent events, then it uses AJAX long polling, and so on. Let's look at how to use SignalR to broadcast information from a function that reads the Azure Cosmos DB change feed. Now that we've tested the application on your local machine, it's time to publish it to the cloud. There are two aspects of your application that require attention before publishing. First, you need to deploy the local functions into Azure, and then you need to make the static HTML and JavaScript files available on the web. Azure Storage includes a feature where you can place files in a specific storage container, which makes them available for HTTP requests. This feature, known as static website support, makes hosting publicly available web pages a simple process. When you copy files to a storage container named $web, those files are available to web browsers via a secure server using a specific URI scheme, which includes the account name, zone name, and the file name. In this module, you updated the design of a stock price service from being polling-based to push-based. The goal was to keep web clients updated automatically as soon as changes to the data were available. First, you learned about the limitations of the existing solution, which looked for stock price changes on a schedule. Then, you replaced polling with a SignalR service-based solution that pushes updates to clients as changes are available. Finally, the solution was deployed to the cloud with the static website hosted in Azure Storage. The solution uses Azure Cosmos DB and Azure Functions in combination with SignalR to detect and broadcast changes in the database. With this new application architecture, your application enjoys the following benefits. An efficient web application architecture, where communication between the client and the server happens only when data is changed. Simple data change detection using Azure Functions to listen to the Azure Cosmos DB change feed via the Azure Cosmos DB trigger. Server push architecture with a wide range of support for new and old browsers via SignalR. Improved response time and reduced to a little over half a second to automatically update the UI. To verify your implementation, you can reference the end folder or you can view the code on GitHub. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this module. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resource you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. And if you created a new GitHub repository for your wiki, you can now delete it. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. The sandbox automatically cleans up your resources when you're finished with this module. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. Follow these steps to remove tenant from configuration. On Windows or Linux, select File, Preferences, Settings. On Mac OS, select Code, Preferences, Settings. Navigate through User Settings, Extensions, Azure Configuration, and clear the tenant in Azure. You do this by deleting the content in the tenant text box. Once the tenant is removed from the Azure Extension settings, open the command palette and select Azure, Sign Out, and then Azure Sign In. Hello. In this lesson, you will learn how to expose multiple Azure Function apps as a consistent API by using Azure API Management. You can use Azure Functions and Azure API Management to build complete APIs with a microservices architecture. Suppose you work for an online store with a successful and busy website. Your developers have written the business logic for the site as microservices in the form of Azure Functions. Now, you want to enable partners to interact with your online store from their own code by creating a web API that they can call over HTTP. You want to find an easy way to assemble your functions into a single API. In this lesson, you will learn how to use API management to assemble multiple microservices implemented as Azure Functions into an integrated web API. In this lesson, you will identify the value of Azure API management in a serverless application, import an Azure Function app as an API in Azure API Management, import multiple Azure Function apps as a single API in Azure API Management. The Azure API Management, or APIM service, enables you to construct an API from a set of disparate microservices. In your online store, you have implemented each part of the application as a microservice, one for the product details, one for order details, and so on. A separate team manages each microservice, and each team uses continuous development and delivery to update and deploy their code on a regular basis. You want to find a way to assemble these microservices into a single product and then manage that product centrally. In this lesson, you'll learn how Azure API Management is useful in a serverless architecture by building single APIs from individual microservices. Let's look at serverless architecture and microservices. Microservices have become a popular approach to the architecture of distributed applications in recent years. When you build an application as a collection of microservices, you create many different small services. Each service has a defined domain of responsibility and is developed, deployed, and scaled independently. This modular architecture results in an application that is easier to understand, improve, and test. It also makes continuous delivery easier because you change only a small part of the whole application when you deploy a microservice. Another complementary trend in distributed software development is serverless architecture. In this approach, a host organization publishes a set of services that developers can use to run their code. The developers do not have to concern themselves with the supporting hardware, operating systems, underlying software, and other infrastructure. Instead, the code is run in stateless computing resources that are triggered by requests. Costs are only incurred when the services execute, so you don't pay much for services that are rarely used. Now let's look at Azure Functions. Azure Functions is a service that enables serverless architectures in Azure. You can write functions without worrying about the supporting infrastructure in many different languages, including C#, Java, JavaScript, PowerShell, and Python. You can also use libraries from NuGet and the Node Package Manager, or NPM, and authenticate users with the OAuth standard from providers such as Active Directory, Facebook, Google, and Microsoft Account. When you write a function, you choose a template to use depending on how you want to trigger your code. For example, if you want to execute the function in response to a HTTP request, use the HTTP trigger template. You can use other templates to execute when there are new messages in a queue, a blob storage container, or on a predefined schedule. When you use Azure Functions in a consumption plan, you are charged only for the time that your code runs. Azure API Management, or APIM, is a fully managed cloud service that you can use to publish, secure, transform, maintain, and monitor APIs. It helps organizations publish APIs to external partner and internal developers to unlock the potential of their data and services. API management handles all the tasks involved in mediating API calls, including request authentication and authorization, rate limit and quota enforcement, request and response transformation, logging and tracing, and API version management. APIM enables you to create and manage modern API gateways for existing back-end services, no matter where they are hosted. Because you can publish Azure Functions through API management, you can use them to implement a microservices architecture. Each function implements a microservice. By adding several functions to a single API management product, you can build those microservices into an integrated distributed application. Once the application is built, you can use API management policies to implement caching or ensure security requirements. When you choose a usage plan for API management, you can choose the consumption tier because it's especially suited to microservice-based architectures and event-driven systems. For example, it would be a great choice for our online store web API. The consumption tier uses the same underlying service components as the previous tiers, but employs an entirely different architecture based on shared, dynamically allocated resources. The consumption tier aligns perfectly with serverless computing models. There is no infrastructure to manage, no idle capacity, high availability, automatic scaling, and usage-based pricing, all of which makes it an especially good choice for solutions that involve exposing serverless resources as APIs. Next, we will create an API management instance and add a function to it. The microservices approach to architecture creates a modular application in which each part is loosely coupled to the others. This method makes it easier to implement continuous delivery because new versions of each service can be deployed independently of the others. If bugs are not detected during testing and make it through to production, their impact is reduced and it is easier to roll back to a stable version. Also, you can create small autonomous teams of developers for each microservice. This division fits well with modern agile practices. However, microservices architectures can also present challenges, such as client apps are coupled to microservices. If you want to change the location or definition of the microservice, you may have to reconfigure or update the client app. Each microservice may be presented under different domain names or IP addresses. This presentation can give an impression of inconsistency to users and can negatively affect your branding. It can be difficult to enforce consistent API rules and standards across all microservices. For example, one team may prefer to respond with XML and another may prefer JSON. Finally, you're reliant on individual teams to implement security in their microservice correctly. It's difficult to impose these requirements centrally. By adding multiple APIs, functions, and other services to API management, you can assemble those components into an integrated product that presents a single entry point to client applications. Composing an API using API management has advantages. Client apps are coupled to the API expressing business logic, not the underlying technical implementation with individual microservices. You can change the location and definition of the services without necessarily reconfiguring or updating the client apps. API management acts as an intermediary. It forwards requests to the right microservice, wherever it is located, and returns responses to users. Users never see the different URIs where microservices are hosted. You can use API management policies to enforce consistent rules on all microservices in the product. For example, you can transform all XML responses into JSON if that is your preferred format. Finally, policies also enable you to enforce consistent security requirements. API management also includes helpful tools. You can test each microservice and its operations to ensure that they behave in accordance with your requirements. You can also monitor the behavior and performance of deployed services. Azure API Management supports importing Azure Functions apps as new APIs or appending them to existing APIs. The process automatically generates a host key in the Azure Function app, which is then assigned to a named value in Azure API Management. In the next lesson, you'll add the order details microservice to the online store API that you created in the preceding exercise. By doing that, you'll integrate order details with the product details microservice and present them both in the same domain as part of an integrated API. In this module, you published a serverless API with 2 Azure Functions apps in an instance of Azure API Management. This approach enables you to implement a microservices architecture by coding Azure Functions as serverless components. API Management assembles these microservices into a single API product using a single URL, all while generating consistent behavior imposed by using API management policies. And finally, a word on cleanup. The sandbox automatically cleans up your resources when you're finished with this lesson. When you're working in your own subscription, it's a good idea at the end of a project to identify whether you still need the resources you created. Resources left running can cost you money. You can delete resources individually or delete the resource group to delete the entire set of resources. For detailed steps on how to delete Azure resources, please refer to the reading at the end of this module. Hello and welcome. In this module, you will have an opportunity to recap key topics and take a practice exam. Let's start by looking at the topics you covered. In this course, you learned how to create serverless applications in Microsoft Azure. You first learned how to automate business processes with Microsoft Azure. Then you explored how to execute an Azure function with triggers. Next up, you chained Azure functions together using input and output bindings. And from there, you looked at how to modernize workflow with Azure Functions. Next was how to monitor GitHub events by using a webhook with Azure Functions. And finally, you explored how to enable automatic updates and build APIs. You saw how business processes can be automated by using Azure Functions, which allow developers to host business logic that can be executed without managing or provisioning infrastructure. You learned how Microsoft Azure provides several different ways to host and execute code or workflows without using virtual machines. These included Azure Logic Apps, Microsoft Power Automate, Azure Web Jobs, and Azure Functions. You learned about these technologies and how to choose the right one for a given scenario. Next, you learned how business processes can be automated by using Azure Functions. This allows developers to host business logic that can be executed without managing or provisioning infrastructure. These Azure Functions can be executed by a trigger. Triggers are used to determine how an Azure function is executed. You explored various trigger types such as HTTP, timer, and blob. This was useful in order to help you determine which trigger works best for your business needs. You saw that the power of Azure Functions comes mainly from the integrations with a range of data sources and services. These are defined by using bindings. With bindings, developers can interact with other data sources and services. You then learned how to utilize bindings in Azure Functions in order to read and store data from Azure Cosmos DB and send messages to Azure Q Storage. You also learned that there are two kinds of bindings you can use with functions: input bindings and output bindings. Next, you explored how Azure Functions can be used to modernize a workflow. In particular, how to use durable functions to orchestrate a long-running workflow as a set of activities. To do this, you use the Azure Functions core tools to create and run functions on a development computer and publish them to Microsoft Azure. You explored durable functions and how you can create and run them on a development computer for testing before deployment to Azure. Finally, you also learned how to develop, test, and deploy an Azure function with Visual Studio. In the monitoring module, you saw how to monitor GitHub events by using a webhook with Azure Functions. Webhooks offer a lightweight mechanism for your app to be notified by another service when something of interest happens. You learned how to trigger an Azure function with a GitHub webhook and parse the payload for insights. Next, you created a function triggered by a webhook and set up a webhook for a GitHub repository. Then you triggered an Azure function with a GitHub event and learned how to secure webhook payloads with a secret. Finally, you explored how to enable automatic updates and build APIs. You examined how to update a web app's notification mechanism from polling to push-based architecture with SignalR Service, Azure Cosmos DB, and Azure Functions. You also learned how to combine multiple Azure Functions apps into a unified interface by importing them into a single Azure API management instance. Congratulations! You have completed this course. You have now covered the key elements of the course, Create Serverless Applications. The topics covered were automate business processes with Microsoft Azure, execute an Azure function with triggers, chain Azure functions together using input and output bindings, modernize workflow with Azure Functions, monitor GitHub events by using a webhook with Azure Functions, enable automatic updates and build APIs, and a practice exam. Demonstrating knowledge of these topics is a requirement in the exam AZ-204, Developing Solutions for Microsoft Azure. You are one step further down the road to certification. In the next course, you will learn how to leverage communication services to create scalable, efficient solutions out of testable components. It will be the next step in gaining more insight into the world of an associate developer with Microsoft Azure and further preparing for the AZ-204 exam.